heat rises. Every person who has ever stood in a room with a fire knows this. The air near the stove is hot. The air at chest height is warm. The air at ceiling height is warmer still. The hottest air in the room, rising on the convective current generated by the stove, pooling against the ceiling in a layer of the warmest air the cabin produces. This is the air the family needs. This is the air the stove labored to create. And in every frontier cabin, this air, the warmest, most valuable air in the room, was in direct contact with the coldest surface in the building, the roof. The roof of a frontier cabin was the weakest point in the thermal envelope. The walls had mass, 8-inch logs chinked with clay and moss, presenting a thermal barrier of approximately R8 to R10. The floor had earth beneath it, packed soil or a crawl space that moderated the cold from below. But the roof was thin. A standard frontier roof was constructed from poles, 3 to 4 inches in diameter, laid side by side across the ridge beam and the wall plates, covered with bark or boards and topped with a layer of sod or shakes. The total thickness of this assembly was 4 to 6 inches, and the R value was approximately R4 to R6, half the insulation of the walls and a fraction of the insulation needed to retain the hot ceiling level air that represented the stove's best output. The result was a thermal chimney effect that operated continuously throughout the heating season. The hottest air rose to the ceiling. The ceiling, with its low R value, conducted the heat rapidly through the thin roof assembly to the cold air or snow above. The hot ceiling air cooled, became denser, and sank, replaced by the next wave of hot air rising from the stove, which also hit the ceiling, also lost its heat, and also sank. The cycle was continuous and devastating. The stove pumped heat upward, the roof dumped it outside, and the family lived in the cooled air that sank back down after the ceiling had stripped it of its warmth. Estimates varied, but the roof accounted for 25 to 35% of total heat loss in a standard frontier cabin, the single largest loss pathway after the walls, and the most wasteful because it preferentially removed the hottest air rather than the average air. Every frontier builder knew the roof was cold. The evidence was visible. Frost formed on the interior surface of the roof poles on cold mornings. Meltwater dripped from the underside of the sod layer when the stove heated the cabin above freezing. And the temperature difference between floor level and ceiling level, which should have been 5 to 8 degrees in a well-insulated room, was 15 to 20 degrees in a cabin with a standard roof, because the ceiling was actively cooling the upper air layer. Kenji Murakami had a solution. It was not a new solution. It was 800 years old. Kenji had arrived in the Cascade foothills of Oregon Territory in the spring of 1887, traveling south from Portland with his wife Haruki and their son Takeshi, who was 10. Kenji was 41 years old, a lean, quiet man with a narrow face weathered to the color of seasoned oak, dark eyes behind wire-rimmed spectacles that had survived the Pacific crossing and 3 years of frontier life, high cheekbones, a thin mouth set in a permanent expression of thoughtful concentration, and the long, precise fingers of a man who had spent his adult life working with wood. In the mountain village of Shirakawa, in the Gifu prefecture of Japan, Kenji had been a daiku, a carpenter, trained in the traditional Japanese building arts that had produced some of the most sophisticated wooden structures in the world. The Japanese understood roofs the way the Georgians understood chimneys, and the Frisians understood beds, not as simple coverings, but as complex thermal systems that could be engineered to manage heat, moisture, and airflow with a precision that Western construction did not attempt. The traditional Japanese Minka, the rural farmhouse of the mountain regions, featured a roof system that was the most thermally sophisticated element of the building. A massive thatched roof, 3 to 4 feet thick, supported on a framework of heavy timbers, with an interior airspace between the ceiling of the living area and the underside of the thatch that served as both insulation and ventilation. The airspace was the critical element. It was not an accident of construction. It was a deliberate thermal buffer zone, a trapped layer of still air that separated the warm living space below from the cold roof surface above, preventing the direct conductive heat loss that plagued single-layer roof construction. The Minka roof airspace worked through two mechanisms. First, still air is an excellent insulator, approximately R1 per inch for a sealed airspace, comparable to snow and better than most solid materials. A 6-inch airspace provided R6 of insulation, which, when combined with the R value of the thatch above, R20 or more for 3 feet of rice straw, and the ceiling boards below, R1, created a combined roof insulation of R27 or higher, vastly superior to any frontier roof construction. Second, the airspace allowed moisture to escape. The warm, moist air rising from the living space below passed through the porous ceiling boards into the airspace, where it could migrate upward through the thatch and escape to the outside without condensing on the cold roof surface and dripping back into the living space. The airspace was both a thermal barrier and a moisture chimney, keeping heat in and water out simultaneously. Kenji looked at the Oregon cabin roofs and saw the same failure he had seen in every Western building. A single thin layer between the warm interior and the cold sky, with no airspace, no thermal buffer, and no moisture management. The frontier roof was a direct conductive bridge between the warmest air in the cabin and the coldest surface on the building, and it was stealing heat at a rate that the stove could not overcome. The cabin that Kenji built in the summer of 1887 was conventional in its walls and floor. Douglas fir logs, 8 inches in diameter, chinked with clay and moss, with a packed earth floor over a bed of fir boughs. The cabin measured 14 by 16 feet, 224 square feet, a modest size that reflected both the practical limits of the available timber and Kenji's preference for a compact, well-built structure over a large, poorly built one. The walls were tight, the chinking was thorough, and the floor was adequate. The roof was where Kenji departed from every other builder in the valley. Kenji built 2 roofs. The first roof, the lower roof, was constructed at the standard ceiling height of 7 feet above the floor. It was a flat ceiling of Douglas fir planks, 1 inch thick, laid tightly across ceiling joists that spanned the 14-foot width of the cabin. The planks were tongue and groove jointed, a technique that Kenji cut by hand with his Japanese planes, producing joints so tight that a knife blade could not be inserted between them. The ceiling was sealed. Not a single gap, not a single crack, not a single pathway for warm air to escape upward. This ceiling was not the roof. It was the floor of the airspace above. The second roof, the upper roof, was constructed 6 inches above the first. It was a conventional pole and shake roof. Douglas fir poles, 4 inches in diameter, laid across the ridge beam and wall plates, covered with split cedar shakes in overlapping courses for waterproofing. The upper roof was the weather barrier, the surface that shed rain, held snow, and faced the elements. Between the lower ceiling and the upper roof was the airspace, 6 inches of still trapped air sealed below by the tight-jointed ceiling planks and enclosed above by the pole and shake assembly. If you want to know what happened when a Japanese carpenter built an invisible room between his ceiling and his roof, while every neighbor said he was wasting good lumber, subscribe to this channel and tell me in the comments where you are watching from. The airspace was not simply an empty gap. Kenji had learned from the Minka tradition that a dead airspace worked best when it was divided into cells, small enclosed compartments that prevented convective circulation within the space. In an undivided 6-inch gap, the warm air at the bottom of the gap, heated by the ceiling below, would rise, contact the cold upper roof, cool, and sink back down, creating a miniature convective loop within the airspace that transferred heat from the ceiling to the roof and reduced the effective insulation value. Kenji blocked this circulation by installing crosspieces, short sections of fir plank, 6 inches tall, placed perpendicular to the ceiling joists at 2-foot intervals across the entire ceiling area. The crosspieces divided the 6-inch airspace into approximately 56 individual cells, each 2 feet by 2 feet by 6 inches, in which the air was truly still, too small for significant convective circulation to develop. The divided airspace had an effective insulation value of approximately R6, 6 times the R1 of a single layer of wood planks, and comparable to 3 inches of modern fiberglass insulation. Combined with the R1 of the ceiling planks below and the approximately R3 of the pole and shake roof above, the total roof assembly insulation was approximately R10, more than double the R4 of a conventional frontier roof, and sufficient to retain the hot ceiling level air, rather than conducting it through the roof and dumping it into the sky. The total cost of the double roof system was $14 above the cost of a conventional single roof. $8 for the additional lumber, ceiling planks, and crosspieces, $4 for the extra ceiling joists needed to support the ceiling independent of the roof structure, and $2 for hardware and miscellaneous materials. The labor, approximately 5 days of additional construction time, was Kenji's own, and it was the most skilled work in the entire cabin build because the tight-jointed ceiling had to be absolutely sealed to prevent warm air from leaking upward through the joints and defeating the purpose of the airspace. The first test came on the evening of November 3rd, 1887. The temperature dropped to 18 degrees, the first hard freeze of the season, and Kenji lit the stove with a moderate charge of Douglas fir at 5 in the afternoon. By 6 o'clock, the cabin had reached 62 degrees at table height, and, here was the difference, 66 degrees at ceiling height. The temperature gradient between floor and ceiling was only 4 degrees, compared to the 15 to 20 degrees that his neighbor's cabin showed, where the hot ceiling air lost its heat so rapidly to the thin roof that it never accumulated. The tight ceiling was holding the warm air in the room. The airspace above was blocking the heat transfer that would normally drain the warmth through the roof. The ceiling surface was warm, approximately 60 degrees, rather than the 45 to 50 degrees of a conventional roof underside, because the heat was staying in the ceiling planks rather than conducting through them into the cold sky. By January, with the outdoor temperature regularly dropping to 10 and 15 below zero, the double roof cabin's performance was confirmed. The ceiling temperature remained within 5 degrees of the floor temperature, a nearly isothermal room that distributed the stove's heat evenly from floor to ceiling, rather than concentrating it at stove level and losing it at ceiling level. The roof-related heat loss, which in a conventional cabin accounted for 25 to 35% of total loss, was reduced by the double roof to approximately 10 to 15%. The stove worked less, the cabin stayed warmer, and the fuel consumption for the first winter was approximately 3 cords of Douglas fir, compared to the 4.5 that a comparable single-roof cabin in the valley consumed. A 33% fuel savings, attributable entirely to the $14 double roof. If this story has touched you, share it and subscribe, because the quiet engineering that kept families alive and farms running for generations deserves to be remembered. The overnight performance was where the double roof showed its greatest advantage. In a conventional cabin, the stove's heat was lost through the roof at the maximum rate during the hours when the stove was hottest, during and immediately after the evening burn, when the ceiling air reached its peak temperature and the temperature difference between the ceiling and the cold sky was greatest. This meant that the stove's best heat, the heat produced during the most active burn, was disproportionately lost through the roof, and the residual heat available for overnight warming was reduced. The family experienced this as a rapid temperature drop after the fire died. The ceiling gave up its heat to the cold roof. The cabin air cooled from the top down, and within 3 to 4 hours, the room was cold. In the double-roof cabin, the stove's heat was retained at ceiling level because the airspace blocked the conductive pathway to the cold sky. The hot ceiling air stayed hot, or at least warm, for hours after the fire died, because the R10 roof assembly conducted heat outward at less than half the rate of the conventional R4 roof. The overnight temperature drop was reduced from 25 to 30 degrees in conventional cabins to 15 to 18 degrees, a significant improvement that pushed the dawn temperature from the mid-30s, conventional, to the mid-40s, double roof. The mid-40s at dawn was not warm, but it was the difference between waking to a cabin where the water barrel had a skin of ice and waking to a cabin where the water was still liquid and the air was merely cool rather than freezing. Haruki's contribution was the moisture observation that led to Kenji's most important refinement. In the second winter, Haruki noticed that the ceiling planks nearest the stovepipe, where the heat was most concentrated, showed dark staining on their upper surface, visible when Kenji lifted a ceiling plank for inspection. The staining was moisture damage. Warm, moist cabin air was penetrating the ceiling joints in the hottest zone, entering the airspace, contacting the cooler upper roof surface, and condensing into water that dripped onto the upper surface of the ceiling planks. The condensation was not reaching the living space below. The tight joints prevented dripping, but it was wetting the ceiling planks from above, promoting slow rot that would eventually weaken the ceiling structure. Kenji's solution was a ventilation modification borrowed from the Minka tradition. He drilled a series of small holes, 1/4 inch in diameter, along the peak of the upper roof, creating a ridge vent that allowed the moist air in the airspace to escape upward and be replaced by dry outside air that entered through small gaps left at the eaves. The ventilation rate was minimal, far too slow to significantly cool the airspace, but sufficient to carry the moisture out before it could condense on the cold upper roof surface. The ridge vent reduced the humidity in the airspace from near saturation to approximately 50%, eliminating the condensation problem entirely and extending the life of the ceiling planks from an estimated 10 years, with moisture damage, to 30 or more years, dry. The ventilation had a small thermal cost, approximately 1 degree of ceiling temperature, lost to the slow air movement through the vented space. But the structural benefit far outweighed the thermal penalty, and Kenji considered the vented double roof to be the perfected version of the design, superior to the sealed version in every respect, except the negligible temperature difference. The neighbor who noticed the double roof first was Amos Caldwell, a Tennessee-born farmer who occupied the adjacent homestead and who visited Kenji's cabin in January 1888 during a cold spell. Caldwell noticed two things immediately. The cabin was warm at ceiling height, unusual. Every cabin he had ever been in was hot near the stove and cold at the ceiling, and the underside of the ceiling was dry, also unusual. Most cabin roofs showed moisture, frost, or drip marks on the underside during winter. He asked Kenji what was different about the roof. Kenji took him outside, pointed to the visible gap between the ceiling line and the roof line at the eave, and explained the airspace. Caldwell looked at the gap for a long time and then asked, "How much extra lumber?" Caldwell built a double roof on his cabin the following summer. His version was simpler than Kenji's. He used rough-sawn planks for the ceiling rather than tongue and groove, which he lacked the tools to cut, and he sealed the plank joints with strips of canvas dipped in pine pitch rather than relying on tight joinery. The canvas-sealed ceiling was not as airtight as Kenji's, but it was sufficient to capture approximately 80% of the benefit. A ceiling temperature 5 degrees warmer than his previous single-roof ceiling, and a fuel savings of approximately 25%. Caldwell did not install the cross pieces that divided the airspace into cells, a simplification that reduced the effective R value of the airspace from R6 to approximately R4 due to convective circulation. But the undivided airspace still provided a significant improvement over the single-roof construction. The February ice storm of 1890 tested the double roof's structural integrity. 3 inches of ice accumulated on the upper roof surface over 2 days of freezing rain, adding approximately 15 pounds per square foot to the roof load, a total of approximately 3,400 pounds on the 224 square foot roof area. The upper roof, built from 4-inch poles at 12-inch spacing, deflected noticeably under the ice load, sagging approximately 1 inch at mid-span, but held without failure. The lower ceiling, which carried no external load, only the weight of the crosspieces and whatever dust and debris accumulated in the airspace, showed no deflection. The structural independence of the 2 roof layers was a safety feature that Kenji had built in deliberately. If the upper roof failed under extreme snow or ice load, the lower ceiling would continue to provide shelter, and the upper roof could be repaired or replaced without disturbing the living space below. The ice storm also demonstrated the moisture management benefit of the ventilated airspace. In conventional cabins, the ice layer on the roof melted from below, heated by the cabin's warmth conducting through the thin roof, and the meltwater seeped through the shakes, dripped through the pole gaps, and rained into the cabin interior. 3 families in the valley reported interior dripping during the ice storm. Kenji's cabin stayed dry. The airspace between the ceiling and the upper roof insulated the ice layer from the cabin's heat, preventing the bottom surface melting that caused the leaking. The ice melted from above when the sun returned, and the meltwater ran off the shakes to the ground without entering the building. By the winter of 1893, 4 families in the valley had built double roofs, Kenji's original, Caldwell's simplified version, and 2 others who had observed the results and commissioned Kenji to build the ceiling assemblies for them at a labor cost of $10 each, materials supplied by the homeowner. Each installation showed consistent results. Ceiling temperatures 5 to 10 degrees warmer than single-roof cabins, fuel savings of 25 to 33%, elimination of interior roof dripping and frost, and a dawn temperature 5 to 10 degrees warmer than comparable single-roof cabins. The construction method that Kenji taught to each family he worked with included the critical details that determined success or failure. The ceiling must be tight, sealed with tongue and groove joinery, canvas and pitch strips, or at minimum, overlapping planks with staggered joints that prevented direct air paths through the ceiling plane. A leaky ceiling defeated the purpose of the airspace, because warm, moist air rising through the leaks would transfer heat by convection, fast, rather than conduction through still air, slow, and the effective insulation value would drop from R6 to approximately R2, barely better than a single roof. The airspace must be at least 4 inches, preferably 6, because thinner spaces allowed radiation heat transfer to dominate, the warm ceiling radiating directly to the cold upper roof across a narrow gap, reducing the insulation value. The ridge vent must be small, 1/4 inch holes at 12-inch spacing, enough to carry moisture out, but not enough to create a draft that would flush the warm air from the space and replace it with cold outside air. Haruki developed a system for using the airspace as a drying chamber during the wet months of autumn and spring. She would open a ceiling plank at one end of the cabin, hang strips of venison, salmon, or fruit on strings stretched between the ceiling joists within the airspace, and replace the plank. The airspace, warm from the ceiling below, ventilated through the ridge vent and enclosed from insects and rain, provided ideal drying conditions that produced jerky and dried fruit of consistent quality without the smoke exposure of traditional outdoor drying, or the space consumption of indoor drying racks. The drying chamber was Haruki's innovation, not part of the Minka tradition, which used dedicated drying rooms, but an adaptation that exploited the double roof's unique characteristics for a practical purpose beyond thermal insulation. Takeshi, who was 10 when the family arrived in Oregon and 23 when Kenji built his last double roof, learned the technique from his father with the thoroughness of a traditional Japanese apprenticeship. Not just the construction methods, but the principles behind them. He understood why the airspace worked. Still air insulates. Why the cells mattered, preventing convection. Why the ridge vent was necessary, moisture management. And why the ceiling had to be tight, preventing convective heat loss. By 1900, Takeshi was building double roofs independently, and his versions incorporated refinements that improved on Kenji's original. Most notably, a double-layer ceiling with staggered joints that eliminated the need for canvas ceiling, and that provided R2 of ceiling insulation rather than R1, raising the total roof assembly to R12. The economics of the double roof over a 10-year period were compelling. Construction cost, $14 above conventional. Annual fuel savings, 1.5 cords at $5 per cord, or $7.50 per year. 10-year fuel savings, $75. 10-year maintenance cost, approximately $0. The ceiling planks, ridge vent, and airspace required no maintenance once installed. Net 10-year benefit, $61, a return of over 400% on the $14 investment. The double roof paid for itself in less than 2 winters and continued generating savings for the life of the cabin. The long-term durability of the double roof system exceeded Kenji's expectations. After 10 winters, the ceiling planks, Douglas fir, 1 inch thick, tongue, and groove, showed no deterioration. The ridge vent, which Kenji had expected might need periodic clearing of accumulated debris, remained open and functional with no maintenance. The airspace, inspected annually by lifting a ceiling plank and looking into the gap, was clean, dry, and structurally sound. the crosspieces firmly in place, the upper roof poles showing no rot or sagging, the entire assembly performing identically to its first winter. Kenji lived on the Oregon homestead until 1909, when he and Haruki moved to Portland to be near Takeshi and his family. The cabin, with its double roof, its tight-jointed ceiling, its ventilated airspace, passed to a neighboring family who maintained both the structure and the practice for another decade. The double roof had operated for 22 winters without failure, without maintenance beyond the annual inspection, and without any degradation of thermal performance. The ceiling had kept the warm air in the room. The airspace had kept the heat from escaping through the roof, and the understanding that Kenji brought from Shirakawa, that the best roof is not one layer between the family and the sky, but 2 layers with still air between them, had been proven on the Oregon frontier as surely as it had been proven in the Japanese mountains for 800 years. The science of still air insulation that Kenji exploited was not unique to Japanese building. It was a universal physical principle that had been discovered independently by builders across the world. But the Japanese application in the Minka roof was among the most sophisticated and deliberate. The principle was straightforward. Air that cannot move cannot carry heat by convection, and still, air has a thermal conductivity of approximately 0.024 watts per meter per Kelvin, lower than wood, 0.12, lower than earth, 0.25, lower than stone, 1.7, and lower than any solid building material available on the frontier. A 6-inch layer of perfectly still air insulated better than 6 inches of solid wood, 6 inches of packed earth, or 6 inches of stone. Better, in fact, than almost anything except animal fur and bird feathers, which achieve their insulation by trapping still air in microscopic pockets between the fibers. The challenge was keeping the air still. Air in an open space moves, heated by warm surfaces below, cooled by cold surfaces above. It circulates in convective loops that transfer heat from warm to cold at a rate many times faster than conduction through still air. An open 6-inch gap between a warm ceiling and a cold roof would generate vigorous convective circulation that would reduce the effective insulation from R6, still air, to approximately R2, moving air. A 67% reduction in performance that made an undivided airspace only marginally better than no airspace at all. Kenji's crosspieces solved this problem by dividing the space into cells small enough that convective circulation could not develop. The physics of convective onset in enclosed spaces followed a principle that modern engineers would call the Rayleigh number, a ratio of buoyancy forces, which drive circulation, to viscous forces, which resist it. In a cell 2 feet square and 6 inches tall, with a temperature difference of approximately 20 degrees between the warm ceiling below and the cold roof above, the Rayleigh number was below the critical threshold for convective onset, meaning the air remained essentially still and the full R6 insulation value was achieved. Without the crosspieces, the Rayleigh number in the full 14-foot wide space exceeded the critical threshold by a large margin, and the resulting convective loops reduced the insulation to R2 or less. The precision of the ceiling joinery was Kenji's signature contribution and the element that most clearly distinguished his work from any Western adaptation. Japanese carpentry, the tradition in which Kenji had trained for 20 years before emigrating, was a discipline of joints. The Japanese joint was not merely a connection between 2 pieces of wood. It was a relationship, a marriage of surfaces that were cut to mate with a precision measured in fractions of a millimeter, without nails, screws, or adhesives, held together by the geometry of the joint itself and the natural expansion and contraction of the wood. Kenji's ceiling joints were not traditional Japanese joints. The tongue and groove was a Western form that he had adopted for its simplicity and appropriateness to the material. But they were cut with Japanese precision, using Japanese planes, kana, that produced surfaces so smooth that they were nearly polished, and joints so tight that the ceiling was effectively a single continuous surface rather than a collection of planks. The Japanese planes that Kenji used were different from Western planes in a fundamental way. A Western plane pushed the blade across the wood surface. A Japanese plane pulled the blade. The craftsman drew the plane toward his body rather than pushing it away, producing a cutting action that was smoother, more controlled, and capable of finer tolerances than the Western push plane. The pulling action allowed Kenji to take shavings of less than 1/1000th of an inch, a precision that was unnecessary for most construction work, but critical for the ceiling joints, where even a small gap would allow warm air to leak upward into the airspace and reduce the insulation value. The seasonal behavior of the double roof revealed patterns that Kenji observed with the attention of a craftsman who understood that wood was a living material that responded to its environment. During the dry winter months, when the cabin air was heated and dehumidified by the stove, the ceiling planks contracted slightly, opening hairline gaps at the tongue and groove joints that allowed a small amount of warm air to enter the airspace. During the humid summer months, the planks expanded, closing the gaps and sealing the ceiling tightly. This seasonal cycling was within the tolerance that Kenji had designed for. The winter gaps were less than 1/32nd of an inch, too small to allow significant convective air movement, but sufficient to provide the minimal ventilation that prevented moisture accumulation in the airspace during winter. The wood itself was acting as an intelligent membrane, more open in winter when ventilation was beneficial, and more closed in summer when sealing was preferred. The snow load on the upper roof was a structural concern that Kenji addressed with the same engineering precision he applied to every aspect of the construction. The Oregon Cascades received heavy snowfall, 60 to 100 inches per winter in the foothills, and the low-pitched upper roof, designed to shed rain efficiently but not optimized for snow shedding, could accumulate 2 to 3 feet of snow during extended cold periods when the temperature remained below freezing and the snow did not melt. 3 feet of wet Cascade snow weighed approximately 20 to 25 pounds per square foot, a total load of approximately 4,500 to 5,600 pounds on the 224 square foot roof area. Kenji's 4-inch poles at 12-inch spacing were rated for approximately 30 pounds per square foot, sufficient for the maximum expected snow load with a 20% safety margin. The insulation benefit of the roof snow was an additional advantage that Kenji had anticipated from the Minka tradition. 3 feet of snow on the upper roof provided approximately R36 of additional insulation on top of the R10 of the double roof assembly, for a combined winter roof insulation of R46, comparable to a modern well-insulated house, and approximately 10 times the R4 of a conventional frontier roof. During heavy snow periods, the cabin's roof was essentially invisible from a thermal perspective. The heat loss through the roof dropped to near zero, and the stove's entire output went to heating the room and replacing the heat lost through the walls and door. This explained the observation that the double roof cabin performed best during the coldest, snowiest periods, precisely when the conventional cabins performed worst. The summer performance of the double roof was a benefit that Kenji had not emphasized, but that Haruki valued highly. During July and August, when the Oregon sun heated the cedar shakes to 120 degrees or more, the airspace between the upper roof and the ceiling blocked the downward transfer of heat into the living space. The ceiling surface remained at approximately 80 degrees, warm but 20 to 30 degrees cooler than the shake surface above, and the cabin interior was noticeably cooler than neighboring single-roof cabins that absorbed the roof heat directly into the living space. The double roof was a year-round insulation system, keeping heat in during winter and keeping heat out during summer, a dual benefit that the single-roof construction could not provide. The cultural resistance to the double roof in the Oregon settlement was milder than the resistance to other immigrant innovations because the double roof was invisible. Unlike the box bed, which looked like a coffin, the straw cellar, which required digging beneath an occupied cabin, or the snow tunnel, which required crawling on hands and knees, the double roof was completely hidden inside the cabin structure. From outside, the cabin looked like any other: log walls, shake roof, stone chimney. From inside, the ceiling looked like a slightly nicer version of a conventional plank ceiling, smoother, tighter, but not visibly radical. The airspace was invisible, hidden between the ceiling and the roof, doing its work in silence, requiring no interaction from the occupants, no special maintenance, no behavioral adaptation. The double roof was, in this sense, the most adoptable of all the frontier thermal innovations. It demanded nothing of the family except the initial construction cost and the willingness to trust that an invisible layer of air could make a visible difference in warmth. This invisibility was both a strength and a limitation. The families who adopted the double roof experienced its benefits immediately and continuously: warmer ceilings, lower fuel consumption, drier interiors, more comfortable mornings. But they often struggled to explain the benefit to others because there was nothing to see. You could feel the warm wall of a snow-buried cabin. You could touch the warm floor of a straw cellar. You could measure the warm air inside a box bed. But the double roof's benefit was an absence: the absence of heat loss, the absence of frost on the ceiling, the absence of the cold upper air layer that plagued conventional cabins. Explaining an absence was harder than demonstrating a presence, and the double roof spread through the valley more slowly than techniques with visible, tangible proof of their effectiveness. By 1900, 7 of the valley's 16 families had double roofs, a 44% adoption rate achieved over 13 years, driven primarily by the fuel savings data that Kenji and Caldwell provided to anyone who asked. The average fuel savings across all 7 installations was 28%, consistent with the theoretical prediction and confirmed by the family's own wood consumption records. The total annual fuel savings for the 7 families was approximately 10 cords of Douglas fir, 10 cords that did not need to be felled, bucked, split, hauled, and stacked, representing approximately 40 days of collective autumn labor redirected to other purposes. The legacy of the double roof extended beyond the Oregon Valley through Takeshi's work. By 1910, Takeshi had built double roofs on 17 structures across 3 counties in the Cascade foothills: cabins, barns, schoolhouses, and a church. Each installation adapted to the specific building, but following the core principles that Kenji had established: tight ceiling, divided airspace, ridge ventilation. The church installation, a double roof over the sanctuary of a small Methodist church in the valley, was Takeshi's most visible project and the one that generated the most comment, because the church had previously been the coldest building in the valley on Sunday mornings and was suddenly, after the double roof, the warmest. The congregation, which had spent winter shivering through sermons in a building that no amount of stovework could heat above 50 degrees, found themselves sitting in 62-degree comfort, and the minister, who had been preparing shorter winter sermons to reduce the congregation's suffering, returned to his full-length format with visible relief. The snow load on the upper roof was a structural concern that Kenji addressed with careful engineering. The Oregon Cascades received heavy snowfall, 60 to 100 inches per winter in the foothills, and the low-pitched upper roof could accumulate 2 to 3 feet of snow during extended cold periods. 3 feet of wet Cascade snow weighed 20 to 25 pounds per square foot, a total load of approximately 5,000 pounds on the roof area. Kenji's 4-inch poles at 12-inch spacing were rated for approximately 30 pounds per square foot, sufficient for the maximum expected load with a safety margin. The insulation benefit of the roof snow was an additional advantage. 3 feet of snow provided approximately R36 on top of the R10 double roof assembly, for a combined winter roof insulation of R46, comparable to a modern well-insulated house, and 10 times the R4 of a conventional frontier roof. The cultural resistance to the double roof was milder than resistance to other immigrant innovations because the double roof was invisible. Unlike the box bed, the straw cellar, or the snow tunnel, the double roof was completely hidden inside the structure. From outside, the cabin looked like any other. From inside, the ceiling looked like a slightly nicer version of a conventional plank ceiling. The airspace was invisible, doing its work in silence, requiring no interaction, no special maintenance, no behavioral adaptation. This invisibility was both a strength and a limitation. The families who adopted it experienced benefits immediately, but they struggled to explain the benefit to others because there was nothing to see. The double roof's advantage was an absence of heat loss, an absence of frost, an absence of the cold upper layer. Explaining an absence was harder than demonstrating a presence. The summer performance of the double roof was a benefit that Haruki valued highly. During July and August, when the Oregon sun heated the cedar shakes to 120 degrees or more, the airspace blocked the downward transfer of heat. The ceiling surface remained at approximately 80 degrees, 20 to 30 degrees cooler than the shake surface above, and the cabin interior was noticeably cooler than neighboring single-roof cabins. The double roof was a year-round insulation system, keeping heat in during winter and heat out during summer. The comparison between the double roof and the other available ceiling insulation methods on the Oregon frontier demonstrated its superiority. The primary alternative was sod, a 6-inch layer of sod on the roof poles, which provided approximately R3 of insulation and significant thermal mass. But sod was heavy, 30 to 40 pounds per square foot, required massively overbuilt roof framing to support, leaked during spring rains as the sod saturated with meltwater, harbored insects and mice that dropped debris into the living space, and deteriorated within 5 to 7 years, requiring complete replacement. The double roof weighed approximately 3 pounds per square foot. The ceiling planks and crosspieces did not leak, harbored no pests, and lasted indefinitely with no maintenance. The second alternative was bark. Birch bark or cedar bark, laid in overlapping courses on the roof poles, sometimes with a layer of moss above for insulation. Bark provided approximately R2 of insulation, was lightweight and waterproof when properly installed, but deteriorated within 3 to 4 years as the bark dried, curled and cracked, opening gaps that admitted rain and snow. The double roof's cedar shakes on the upper roof provided superior waterproofing with a lifespan of 15 to 20 years, and the airspace below added 6 times the insulation of a bark layer. The third alternative, and the one most commonly used in the valley, was simply accepting the heat loss and burning more wood. This was the default approach of every cabin that did not have a double roof, and it worked in the sense that the family stayed warm, but at a cost of 1.5 additional cords per winter. $45 over 10 years in fuel alone, plus the labor cost of cutting, splitting, and hauling the additional wood. The double roof's $14 construction cost was recovered in fuel savings within 2 winters, making it the most economically efficient thermal improvement available to any frontier builder with basic carpentry skills. The wind behavior around the double roof during storms revealed an aerodynamic benefit that Kenji had not designed for, but that contributed to the cabin's performance. The low-pitched upper roof, which Kenji had designed with a shallow pitch to retain snow for insulation, also presented a low profile to the wind, reducing the aerodynamic forces that drove pressure infiltration through the cabin walls. A conventional steep-pitched roof created a high-pressure zone on the windward side of the cabin and a low-pressure zone on the leeward side, driving cold air through the windward wall cracks and sucking warm air out through the leeward cracks. The low-pitched double roof reduced this pressure differential by approximately 30% because the wind flowed more smoothly over the low profile rather than creating the turbulent eddies that a steep roof generated. The reduced infiltration was a bonus, not the primary purpose of the design, but a measurable benefit that further reduced the cabin's total heat loss. The annual inspection protocol that Kenji established for the double roof was simple and took less than an hour. Each September, before the heating season began, Kenji lifted 3 ceiling planks, one at each end and one in the center, and visually inspected the airspace. He checked for moisture damage on the upper surface of the ceiling planks, none after the ridge vent was installed, for pest activity in the airspace, occasional mouse intrusion addressed by placing a small piece of wire mesh over the eave openings, for structural integrity of the cross pieces and upper roof poles, no issues in 22 years, and for debris accumulation that might block the ridge vent openings, cleared with a stiff brush. The inspection confirmed that the system was functioning properly, and the planks were replaced, and the cabin was ready for winter. The teaching of the double roof technique to other builders required Kenji to translate Japanese building concepts into terms that Western carpenters could understand and execute. The most difficult concept was the importance of the tight ceiling joint. Western frontier carpentry valued speed over precision. A cabin that could be built in a week was preferable to one that took 2 weeks, even if the faster cabin leaked heat. The idea that 5 additional days of careful ceiling work would save 1.5 cords of wood per winter for 20 years was not intuitive to builders trained in the get-it-up-fast tradition of frontier construction. Kenji demonstrated the principle by having doubters hold their hand near the ceiling of his cabin and then near the ceiling of a conventional cabin on the same day at the same outdoor temperature. The 5 to 10 degree difference was immediately palpable and permanently convincing. The legacy of the double roof in the Oregon Cascades was quiet but lasting. The technique did not bear Kenji's name. It was not called the Murakami roof or the Japanese roof, but simply the double roof or the airspace roof, a generic description that stripped the innovation of its cultural origin and made it a local practice rather than an imported one. Kenji did not object to this anonymity. He was a craftsman, not a promoter, and the success of the technique, measured in warm ceilings, dry interiors, and reduced fuel consumption across 7 families and eventually 17 buildings, was satisfaction enough. The double roof worked. It worked because the physics were right, because the construction was precise, and because the principle, still air insulates, was as true in the Oregon Cascades as it had been in the mountains of Gifu for 800 years. The comparison between the double roof and the other available ceiling insulation methods on the Oregon frontier demonstrated its superiority. The primary alternative was sod, a 6-inch layer of sod on the roof poles, which provided approximately R3 of insulation and significant thermal mass. But sod was heavy, 30 to 40 pounds per square foot, requiring massively overbuilt framing, leaked during spring rains as the sod saturated, harbored insects and mice, and deteriorated within 5 to 7 years, requiring complete replacement. The double roof weighed approximately 3 pounds per square foot, did not leak, harbored no pests, and lasted indefinitely with no maintenance. The second alternative was bark, birch or cedar bark in overlapping courses, sometimes with moss above. Bark provided approximately R2, was lightweight and waterproof when fresh, but deteriorated within 3 to 4 years as it dried, curled, and cracked, opening gaps that admitted rain. The double roof's cedar shakes provided superior waterproofing with a 15 to 20-year lifespan, and the airspace added 6 times the insulation of bark alone. The third alternative was simply accepting the heat loss and burning more wood. This was the default approach, and it worked in the sense that the family stayed warm, but at a cost of 1.5 additional cords per winter, $45 over 10 years in fuel alone, plus the labor of cutting, splitting, and hauling. The double roof's $14 cost was recovered in fuel savings within 2 winters, making it the most economically efficient thermal improvement available to any frontier builder with basic carpentry skills. The wind behavior around the double roof during storms revealed an aerodynamic benefit that Kenji had not designed for, but that contributed to performance. The low-pitched upper roof presented a low profile to the wind, reducing the aerodynamic forces that drove pressure infiltration through the cabin walls. A conventional steep-pitched roof created high pressure on the windward side and low pressure on the leeward side, driving cold air through windward cracks and sucking warm air out through leeward ones. The low profile reduced this differential by approximately 30%, because the wind flowed smoothly over the shallow pitch rather than creating turbulent eddies. The reduced infiltration was a bonus that further lowered the cabin's total heat loss. The spreading of the technique through Takeshi's work after 1900 demonstrated how the double roof adapted to different building types and scales. His most notable project was the double roof over the sanctuary of a small Methodist church in the valley, previously the coldest building on Sunday mornings, where no amount of stovework could push the temperature above 50 degrees because the large open ceiling acted as a massive heat drain. After Takeshi installed a double roof ceiling with a divided airspace, the sanctuary maintained 62 degrees during winter services. The congregation, which had spent winters shivering through sermons, found themselves sitting in genuine comfort, and the minister, who had been preparing shorter winter sermons to reduce the congregation's suffering, returned to his full-length format with visible relief. The barn installation that Takeshi completed in 1903 demonstrated the technique's applicability to agricultural structures. A dairy barn with an open cathedral ceiling lost heat so rapidly through the roof that the milk froze in the pails on the coldest mornings, and the cows, which generated significant body heat, but could not overcome the roof loss in the large open space, showed reduced milk production during cold snaps. Takeshi installed a flat ceiling across the barn at 10 feet, creating a 6-inch airspace beneath the existing pole and shake roof, and the barn temperature improved by 8 degrees. The milk stopped freezing. The cow's production recovered, and the farmer calculated that the hay savings from cows that burned fewer calories maintaining body temperature and therefore ate less paid for the ceiling installation within a single winter. Each of these adaptations confirmed the universality of the principle that Kenji had brought from Shirakawa. The double roof was not a trick or a technique specific to a particular building type, climate, or culture. It was an application of a physical law, still air insulates, that worked in any structure, at any scale, in any climate where the roof was a significant source of heat loss. The Japanese Minka, the Oregon cabin, the Methodist church, the dairy barn, each was a different building solving a different problem, but the solution was the same in every case. 2 layers with still air between them, catching the heat before it could escape through the roof and giving it back to the room below. No myths, no miracles. Just 2 roofs, 6 inches of still air, and the understanding that heat rises. And the best ceiling is the one that catches it before it leaves.